I'll wait just for a couple of minutes or seconds. Compliments to the chairman because he pretty much nailed my surname. I'm Iztok Šušteršič, so it's quite a tongue breaker, but for future notice. So let's just wait a few minutes because I'm a bit anxious to start, because when you have last minute preparations you usually find out that you wait over time, so you can get within 15 minutes only if you talk really, really fast. So I apologize in advance to anybody who might slip something, and pretty much open to questions until the end of the conference or later via my email. So okay, I'm green. So my presentation is titled "Influence of the Connection Behavior on the Seismic Resistance of Land Buildings." The paper was written by myself, Professor Massimo Giacomo, and Dr. Bruno Deutsch. Just a short overview of what I should try to show you today. We should basically go through the methods that current codes and standards offer to a designing engineer who is dealing with seismic design. So basically it's going to be a linear model response spectrum analysis, and I should try to show you the importance of the correct stiffness assessment, as Robert has just pointed out. Then we should move to the nonlinear static, or so-called pushover analysis, with the modified N2 procedure. N2 is the displacement-based design method incorporated into Eurocode for the last 8 years. Then we should move to the nonlinear dynamic time history analysis, and in the end I should try to tell you something about the overstrain factors, which should be used when dealing with cross-lamming. This shall all be demonstrated on a case study building. This is not an actual building, it's, we've thought of it in the last 2 years and we're doing some analysis on it. I won't be talking about it too much because it's all written in the paper, just maybe a few short things. So we were using the same type of connectors across the whole building, BMF 105s, basically because those were the only connectors that we've had some proper experimental response for, so hysteresis response. The perpendicular walls are connected with self-tapping screws. We took on the assumption of a rigid floor diaphragm, and we've designed to 0.25 G, which is the peak ground acceleration in Slovenia, we can expect, and we presume ground type A according to Eurocode, which means solid rock. And we've designed it to an elastic response, so a Q or an R factor in America 1. We should later see why. So the initial number of connectors, which can be seen here on the on this figure, is for the wall B as it follows. Now I just want to point out one last thing. So all the linear elastic analyses are done on the full 3D structure, and the nonlinear ones are done only on wall B. So if we start with the linear elastic analysis, there was a lot of talk about displacement-based design for the past few days, and of course it's very important, but I just want to stress out we should not underestimate still the importance of the linear elastic model response analysis. Displacement-based design gives us lots of information, especially in the nonlinear area. However, if we have if we're dealing with torsion, or we're dealing with higher vibration modes of higher buildings, displacement-based design has to be also corrected with correction factors that come from the model response analysis. So let's not underestimate the power or the influence of the model response analysis, which is actually not as simple as it may seem at first glance for crossland. Why? Crossland walls basically behave in two different ways. Either they slide, so shear, or they bend. They pretty much rock. And they rock around, more or less around corners. The shear response, or the sliding response, is equal in the same directions. You push the wall in one direction or the other, you get more or less the same response. However, if you bend the wall, you get either very high stiffness in compression, which is, you see, this is a hysteresis response of a hold down. So you have very high stiffness in compression, and you have tension stiffness of the connector, whatever it may be. And there's a difference. Even if you use a substitute stiffness for tension and substitute stiffness for compression, they are different. So if you want to model the connections with linear connectors, so basically with springs, you have to use bilinear elements. But bilinear elements cannot be used in the model analysis, because you have to have one single matrix, therefore you have to have one single stiffness. So basically you have to translate this wall behavior like shown in this figure. So we move from the tension stiffness of a bracket to a compression stiffness of the wall, or if you want to call it the bracket, to a equivalent response of a new calibrated bracket, which responds the same in shear and tension. Therefore, it allows for a unified matrix, if you want to call it so. But the basic idea is that the rotation that we get from, or the translation we get from rotation in the properly modeled load case, the properly modeled wall, equals the one that we get at the recalibrated situation. Now that's quite tricky and it's quite a painstaking procedure, so later on I shall be just slightly showing you a new procedure that we've come up with that simplifies all that. But in the meantime, I want to show you the what happens if the periods or the stiffness is assessed wrongly. Now, three very simple buildings. The blue one represents the one where we have a completely stiffly modeled structure, so that's something that probably some engineers that are dealing with concrete will do because they're used to modeling everything stiff. This is what actually should be done, so we should take into account the influence of connections, and this is just an upgrade of the second model. So we also take into account the connections between the perpendicular or the adjacent walls. Now in our case, that's only in 4 places, only in the corners of the structure, so maybe the small difference between models 2 and 3 is not very characteristic of the average cross-link building, however. So we see that the vibration periods for the stiff model are very low, very short. So the wall is very stiff, you know, it vibrates very, very quickly. Both cases with the connectors, of course, are more flexible and therefore result in higher vibration periods. What does that mean for base shear? Well, even though this one is actually modeled, I can, you know, easily say wrong, it actually results in the forces on the conservative side. It actually results in about 50% higher base shear. That only happens because most of the vibration periods of the stiff structure end up in the plateau of the acceleration spectra. However, for displacements, because of that very stiff structure, we end up with very, very low displacements. Now, in the case of Eurocode, where we actually have to check the story drifts for every kind of structure, be it steel, concrete, or timber, this results in about a factor of 4 to 5 of underestimated displacement. So the stiffness is very important, and to avoid the painstakingly long calibration procedure, we've come up with this simplified method. I'm really going to fly for this because this is going to be presented at this year's CIB. So this is the basic idea. If you have, like, you know, this is a proper picture of a cross-link wall setup. So you have the brackets top, bottom, the connections, and the opening. If we model that very precisely with FE elements, we end up with something like this. And the first step of simplification would be, so we try, you know, we cluster the connections in corners, and we don't use the shells for the panels, we use substitute diagonals, and the final stage would be just to squeeze that all up into one substitute diagonal, or of course also one substitute frame. Very simple equations, just fly for this. So this is all stuff that's been done in the past few years, slightly modified, and it's basically it can be put into Excel. So you can get, you know, from very basic characteristics, you can get a substitute stiffness of a wall that you can later put into your FEM model. Same goes for strength. It also allows for a very simple application of the overstrength factors. But as I said, more on this if anybody's coming end of August to CIB. Just a short word on the precision. We're at about 80% precision, which is quite satisfactory for seismic. We can still do something about it, but nevertheless. Okay, I have to move to the pushover analysis. I've decided to put a slide in because some of you may not be well acquainted with the displacement-based design, but it's actually very simple. So this is the pseudo-acceleration spectra, which pretty much everybody who's dealing any time with seismic analysis knows. This is the pseudo-displacement spectra, not that common in engineering practice, but if we put those two together, we have this so-called AD format spectra. So the acceleration displacement spectra. We have the displacement on the x-axis and acceleration on the y-axis. And the vibration periods in this case are characterized by the linear functions that you can see here in gray. Now, keep in mind, so displacement on x, acceleration on y. If we make a pushover analysis of a multi-degree of freedom system, therefore a building, we get displacement on the x and forces on y. Then we transform that pushover curve to a bilinear curve. Here is where we made our slight modification. We weren't using the typical bilinear procedure that's prescribed in Eurocode. We made some modifications that we have sort of found out to be more proper. So you get from a linear curve to a bilinear one. And keep in mind, so you have displacement forces. If you divide the force by the mass, you get acceleration. Now, maybe you see the bigger picture. You have displacement on x, acceleration on y. And you have both curves on the same graph. What does that mean? So you have the elastic spectrum, inelastic demand spectrum. Now, the thing is, the difference between the two is the reduction factor. That's based on building ductility and vibration period. Now, buildings that have short vibration periods are very prone to hysteresis response. And all the equations currently in the Eurocode are more or less devised for concrete and steel structures which have more full hysteresis behavior. Timber structures exhibit pinching, exhibit slip, strength degradation, etc. However, if we're dealing with multi-storey construction, which have longer periods because higher buildings have longer periods, we are in the area where the demand spectrum is less prone to hysteresis behavior. So if I draw our capacity curve, you can see that this is our vibration period of the single degree of freedom system. This is our target displacement where our capacity curve meets the inelastic demand spectrum, and this is our ultimate displacement. So very graphical, very clear. That's probably one of the reasons why displacement-based design also has probably a bright future in the future of engineering, or some engineers are a bit afraid of it. So what we were doing is that we did a few analyses. For example, one was with the third response cycle backbone. The other one was with the first response cycle backbone. So the difference between the two strengths is about 25%. And then we also took into account a friction coefficient of 0.4 between walls and plates. So to see what happens. These are the pushover curves we got. So the blue one represents the first cycle response, and the third one, the third cycle response. The dashed lines are for cases without friction error, the full lines are for friction. So you can see that using a stronger bracket, of course, results in a higher peak base shear. However, the ductility is about the same. So the maximum displacement we reach is about on the same level. Let's just focus on the last line of the table. So this is the maximum ground acceleration that we've come up with from our nonlinear elastic analysis, and it's divided by the 0.25 we're using at the beginning for the linear elastic analysis. So in a way, this is a simplified version of the reduction factor, the Q factor or the R factor. And the values we've come up with were between 2.1 and 2.44. Former analysis done on cross-lamp were done with walls made out of several narrower, adjacently connected walls, and the Q factors for that were about 3, 3.5 and so. So, considering we have here monolithic walls which are larger and have less dissipation areas because we don't have the vertical joints, this sort of seems to correlate. However, of course, there are wall analyses that need to be done. And if I move to the second to last chapter, the non-aerodynamic analysis, we were strictly following the Eurocode 8 procedure, so the accelerograms here are just based from the Eurocode strong motion database, scaled. They were not correlated to fit the spectrum better, so they came as they came. We were using the Rexel software to pick them out. We were also using SAP to model nonlinear time history analysis, so the hysteresis behavior it's not perfect, but it's sort of there. And just an example of what happens, this is our strong motion, this is our peak, this is our top displacement. You can see that if we use friction, the damping seems to be, there seems to be more damping than if we neglect friction. So the structure is still swaying after the strong part of the ground motion is over. So just a short comparison, if we weren't using friction, the average displacement after all the 7 accelerograms was 44 millimeters. If we compare that to the results from displacement-based design, we are quite close. However, if we use friction, we shoot off by about almost 50%. But still, SAP is not the best tool for nonlinear dynamic analysis, especially if you're using very specific hysteresis behavior. And just a short word on the overstrength factors. So I shan't be going into details because I don't have the time, but we've come up with those values. Unfortunately, the number of specimens tested was very, very small, so though these numbers actually correlate quite well to what some other researchers have come up with. The angular brackets exhibit a overstrength factor of 1.3 and the screws of 1.6. So what does that mean? For example, we have a wall with an opening. If we have walls without openings, crosslength is pretty much, we can say, indestructible comparing to connections. But if we have large openings, therefore we have like moment-resistant frames, we can have concentrations of stresses in the corners. So we must take care that we don't have a brittle failure, which technically a rupture of crosslength would be, but that we have ductile failure in our ductile steel connections. So if this would be the curve where we would take the nominal strength of the brackets, this is where we would end up with. So we have, we have the initial stiffness, then we have the plastification, and then the structure pretty much collapses. But in the brackets, however, if the brackets, I'm on red just a second, if the brackets are 30% stronger, then the problem is that they don't actually get the chance to non-linearly, so to ductily fail, because crosslength fails before that. Crosslength fails at about 20.4 kilonewtons, so our frame would break before we would actually get a chance for a ductile dissipation of energy. Just the conclusion, so when we're performing any kind of seismic analysis, it's very important to account for the influence of connections, correct stiffnesses, frictions, and so on. There is a possibility of a simplified method for the linear response spectrum design. We've shown the possibility to use the nonlinear displacement-based design on crosslength. Of course, more work needs to be done on that. And we've shown some overstrength factors for the crosslength. So with that, I conclude my presentation. Thank you very much. So for the question.
Thank you very much, Iztok. It was a very interesting presentation, and it's always good to be a chairman, so I can ask the first question. And we are now involved in some preliminary designs of these CLT buildings, and what we call RDR not factors, pretty much an overstrength factor in Canada and United States. Arjo Čekoty was kind of saying 1.5 or 2, kind of 3. You were saying 1.6. In Canada, FP Innovations they're telling us about 3. What is the number that you would use for design?
I think to keep on the safe side, I would sort of stick to 2.0. I think that's also the value that's in the New Zealand code that's prescribed for timber structures. So I'm guessing that they've sort of done some more analysis generally, because we're only dealing here with brackets. So it's not that we don't have the nails or anything. We just have to make sure that.
So you don't have hold downs?
Of course, we can have hold downs, but let's say in our design practice, we often tend to simplify unless we have some very walls that are very stressed. We just use the same bracket to simplify the design procedure. So we often just use the BMF 105s, but of course that's for the maybe 1 to 2 maximum 3-story buildings. Of course, when you come to more stories, we have to use hold downs.
You see, like in Canada, we would always stick the hold downs even in 1 or 2-story buildings, and that's the standard practice. And what about the rocking shear walls? Would you rather hold your CLT building, or would you rather let it rock?
I technically would not have anything against rocking, because the second order effects with crosslength are not really that. Crosslength is not that prone to second order effects, because you mostly have very long shear walls that won't collapse if you have too large story shear. And rocking also allows for additional energy dissipation, and by itself is a self-centering mechanism. So I would definitely say try using that.
Okay. Any other questions? Here you go.
Yeah, talking about rocking walls, like if you are on the bottom of a 5-story building, there's a huge amount of gravity load coming down. So how do you expect the road can rock? How much rock are you expecting?
Well, of course, it depends on the story height and the mass of the structure. But from the tests that were conducted, for example, at my faculty, it was almost 6 years ago, even for very high loads on walls, of course, you have to take into account as well that a wall can only take so much vertical load before the actual wall buckles. The rotation point was pretty much in the 0.9 length of the actual wall length, but we were testing walls at around 2.5 meters, so it didn't seem to move significantly. However, this is more, I think, a question if you have a high-story building, but in the first floor, where you don't have a concrete foundation anymore, but you have a cross-land plate, which is then actually compressed perpendicular to rain, and then in this case you might end